All right, guys, we're up. The displacement vector in meters of a body from a fixed point O at time t is given by the following formula. So S equals 3t squared minus 1 plus 100 minus 4t cubed. So if you were to, you could put that in your table function, couldn't you? You could put both of them separately into your table function. You know what I'm saying? You could put down f of x is 3x cubed minus 1. And then you could also put down g of x is 100 minus, 4x cubed. Okay? So for argument's sake, the answer after 3 seconds, what your calculator will show you is it'll go x value of 0, 1, 2, and 3. And then you'll have fx here and you'll have gx here. And what it'll tell you for fx is sub in 3. So it's going to be 3 times 27 take away 1, which is 80. And then on the other one, it's going to be 100 take away 4 times 27. So minus 8. Okay. Then it's asking me for the displacement vector. So what does that mean? S is 80i, which means 80 across, and minus 8 down. Any questions thus far? Cool. Okay. Find the velocity vector. How do you think you're going to get a velocity vector? How do you usually change displacement into velocity? What would you do? You differentiate. So let's differentiate both parts. So differentiate that. What do we get? Huh? Just 9t squared, yeah. That's my I components. And then differentiate the j components. Yeah. There you go. Done. Okay. Find the speed of the body at time t equals 3. So the first thing we're going to do is we're going to sub in t equals 3 to get the velocity, not the speed, just the velocity. So I'm going to sub in t equals 3 here. 81i. Yeah. What else? 108j. Okay. Minus 108j. Okay. And then we're going to square them out. Let me know what you get. That's for the velocity because you're doing Pythagoras theorem to find the speed components. 135 meters per second. You cool with that? All right. Find the acceleration at any time. What do you reckon we're doing now? Differentiating velocity. Once you differentiate velocity, what do we get? AT&T, I wrote that down wrong. AT&T I minus 24 TJ. And it would be measured in ms minus 2. Okay, what does one from stand? The magnitude of the acceleration at 10. So what do you think I'm going to do with this? Sub in 10. So I'm going to sub in 10. What you get? 180 I minus 240 J. We kill with that? And then we're going to Pythagoras theorem that to get the magnitude, okay? So let's get the magnitude. So what do we get? Okay, I'm hoping for 300. Does anybody else get 300? Okay. Let's do it. Okay, guys. So Your displacement vector, or sorry, your distance, or sorry, your displacement vector is this one here. Velocity is the first derivative of displacement. So we're going to differentiate this whole thing. So velocity is ds dt. So the first thing we're going to do is, r is a constant. The only variable is t. Does everybody see t? T is the variable. Omega, which is your constant angular velocity, is a constant. So the ones I have highlighted in yellow are constants, and the only thing that's a variable is the cos, is the t, right? So let's treat it as such. So what happens when you differentiate cos omega t? What does cos turn into? Minus sine omega t, yeah? But then you have to differentiate the angle. Did you get omega? Okay. So who in the class got a velocity is, what's it, minus r omega sine omega t. And that's your I components, yeah? Now you got to do your j components. What does sine turn into? Cos. So it'll be plus r omega cos omega t j. Okay, pause here. Now it wants the magnitude. So you ready? Now it wants us to do Pythagoras' theorem. So we're going to go square root, and we're going to do minus rw sine omega t squared, and we're going to do plus, oh sorry, I need another bracket. Unless I just don't bracket it. Bracket the angle. No, I'll bracket the end, yeah. Need to bracket that stuff. And then it's rw cos wt squared. Right. So what do we get out of that then? Anybody? R squared, w squared, yeah, omega squared, sine squared, omega t. And the other side? What do we think we get in the other one? R squared, omega squared, cos squared, omega t. What can we factorize out the both of them? R squared, omega squared, yeah? And what do you think the last bit equals then? What does it equal 1? Sine squared any angle plus cos squared the same angle gives me 1. Oh, this is cool proof. So it's actually the proof of phi equals r omega. So you could be potentially asked that. Here's a vector proof that phi equals r omega. So you turn that into 1, and then you're just left with r squared w squared. And do you remember we learned that velocity equals square root of that? R omega. That's one of our circular motion formulas. The very easy section of circular motion. Phi equals r omega. Cool. So, magnitude done. Find the acceleration vector. Well, I already have the velocity vector, don't I? So I'm going to differentiate that yellow part first. So I'm going to differentiate this because acceleration is the derivative of velocity. So what are we looking at here? Sine turns into cos. Differentiate the angle, kicks out an extra omega. So it's going to be minus r omega squared cos wt. Okay. What does cos turn into? Anybody? Minus sine. I'll linger that minus further away from it like this. So it's going to be cos minus sine omega t. Differentiate the angle, extra omega. So r omega squared t. And I've made a mistake. Who cares to tell me what my mistake is? I didn't put the vectors in, did I? So I did all the differentiation right, but I neglected to put the vectors back in. Okay, so just be careful about that. Now, what does it want from me? Magnitude. So we're gonna have to do the square root thing again. Just because it's such great fun. So it's gonna be minus r omega squared. Here we go. So are we all good for a shortcut here? We're going to do the same thing again, aren't we? We're going to factorize out what? It's going to be cos squared omega t plus we knew that was coming. So what do we know that that's 1, don't we? So it should be the square root of r squared omega squared. Then we get r omega squared. Now, oh, you're going to love this one. So we've proven that, yeah? Tick. Happy days, right? So, prove that at all times the acceleration is perpendicular to the velocity. All right, I should be all right at 43%, but we'll stop now. Prove at all times the acceleration is perpendicular to the velocity. Do you all remember the dot product? Anybody remember the dot product? Okay, let's see if we can remember the dot product, right? Would you all agree that, generally speaking, the slope of 3 over 4 would result, you need a slope of minus 4 over 3 to make sure that they're perpendicular to each other. Is that right? Okay. So, what was the rule for the dot product? Can anybody tell me? Well, so I'll give you an example, right? 3i plus 4j multiplied by minus 4i plus 3j. What happens when a dot product is perpendicular? What happens when you multiply it out? 3 times minus 4. You multiply the coefficients of the I. Then you multiply the coefficients of the j. And what should happen? It equals 0, doesn't it? So when they're perpendicular, t equals 0. So what we're going to do is we're going to extend this knowledge to our velocity and our acceleration. So our velocity vector, so we're going to dot product our velocity vector and our acceleration vector. So velocity vector, wherever it's hiding, here it is. Velocity vector is minus r omega sine omega t I plus r omega cos omega t j, and we are going to dot product that with the a, and the a1 was minus r omega squared cos omega t plus minus. Thank you. I forgot my I, didn't I? Sine, yeah. This should not be done first thing on a Monday morning. Now, did we all get this part here? Multiply by this part here. All right, how many R's are we looking at? R squared omega 3 sine WT cos omega T. Okay, and then we're looking at this one multiplied by that one. So what do we get this time? Minus R squared omega cubed sine omega T cos omega T. And what does all that equal then? 0. 0 equals 0. Because the dot product is 0, this means that these two vectors are perpendicular. Happy days, right? Yeah. Now, explain how you can tell the acceleration is directed towards C, which is the center of the circle, at all times. Well, this is a trick that I would know because I've done it a couple of times, but until you've seen it the first time, you just don't know it. The trick is to relate area, to relate acceleration back to the original equation. Everybody see the original equation with the R omega squared? Okay, so here's what I'm going to do. I'm going to factorize out minus omega squared, and look what happens. See the way I factored out minus omega squared, yeah? And what you're going to be left with is R cos omega T plus R sine omega T. And I forgot my I and J again, didn't I? Love doing that. Now, what can we say about this formula here? What's it the same as? Same as distance. So, A equals minus omega squared S. Sometimes it's known as minus omega squared X. Okay? And what can we say about this? Well, what we're saying is A, acceleration A is in the same line as S. Now, the reason why it's in the same line as S is it's just a constant multiplied by S. See the constant? It's a constant multiplied by S. But does everybody note the minus? The minus means it's in the opposite direction. So displacement is your distance away from the center, but because acceleration is minus, it's aiming back towards the center. It's just a difference in the sign. Minus is away, and sorry, plus is away, minus is back towards. Okay, so that's your official line there. Same line as S, but directed in the opposite direction. I towards C.